Hello, in this video today we're going to learn about electricity and charges. More specifically, we're going to learn about electrostatic charges, properties of electrostatic fields, electric charge in terms of a coulomb, electric field line diagrams and properties, parallel plates and positive-negative point charges, electric fields as the strength equal to the unit at a specific point, electric current, direct and net flow current, and solving equations on fields. First of all, electrostatic charges. In an atom, there are positive protons and negative electrons. The proton is oppositely equal to the negatively charged electron. This makes the protons and electrons balance out and makes the entire atom a neutral charge. If electrons are removed, the entire atom becomes positively charged. The inverse is true if a proton is removed. Negatively charged electrons are attracted to the positively charged protons. Like charges repel one another, as shown in this diagram. In this video we can see electrostatic fields at work. Let's go into a bit more depth so we can understand what's going on. As we can see, the negatively charged cup is pulling towards the positively charged protons, bending the water if you will. It's really just attracting the positives. Electrostatic charges have electrostatic fields. The magnitude of an electric field is directly linked to the electric field strength. It has a force per unit charge being newtons per coulomb. An equivalent unit is volts per meter. As we can see, energy equals newtons per coulomb, which also equals volts per meter. A coulomb is defined as the charge carried past a point per second by 1 ampere of current. We can see this in the diagram to the right. What exactly is going on in a field? Well, we can see that we've got lines that go outwards from a positive charge and lines that go inwards from a negative charge. What does this mean? E in this diagram is the electric field. Q is what we call the test charge, or a point in the field, and the test charge is always positive. Now remember what we said before about positive repelling positive and negative repelling negative? Because the test charge is always positive, a positive field will always go outwards. More lines on an electrostatic field diagram means it's a stronger field. The positive test charge means that the negative field attracts, as explained before. The further out we are from a field, the weaker the force. Hence it has an inverse square law. Here we have some examples of parallel plates and positive-negative charge points. I want to ask you if you can spot out what example is the one shown before with the cup and the water. Number one, of course, being a positive-negative field charge. As we can see, the field attracts to the negative as it's going outwards from the positive and coming into the negative. Example number two is a positive-positive field charge, as both are repelling one another. Number three, which you possibly guessed is the cup and water experiment, is a plate/positive field charge, and number four is just parallel plates. Now, electric field vectors. An electric field vector is the relationship between field strength being equal to the force per unit charge at that point, the same inverse square law in the diagram before. As explained before, energy equals force per unit of charge, which equals newtons per coulomb, which also equals volts per meter. Hence, all three of these energy types can be shuffled around for the product required. I've created three formula triangles here, and I've just put in my own multiplication and division to what the shuffle would require. We'll go into more depth later. Now, electric current. Electric current is the rate in which charge flows under the influence of an electric field. Direct current, or DC current, is the net flow of charge. It travels in one direction, as seen in the diagram below, just a straight line. Alternating current, on the other hand, has a net flow of charge, alternating, moving back and forth periodically, as shown in the other diagram below. Now it's time for solving field equations. Our first equation, an electron has a charge of 1.6 times 10 to the power of negative 19. It is placed in an electric field strength of 2 times 10 to the power of 5 in a northerly direction. Calculate the electric force on the electron. In any information given, I find it best to lay it all out in a linear equation so that we can figure out what we have to shuffle in order to find our unknown value. In this instance, we have charge and energy. To shuffle the formula as required, we find out that F equals energy times charge. We sub in our original values, and then we calculate to find that F equals 3.2 times 10 to the power of negative 14 newtons in a northerly direction. The equation is much like the first. An electron with charge 1.6 times 10 to the power of negative 19 has an electric force being applied on the electron of 3.2 times 10 to the power of negative 14 in a southerly direction. Calculate the field strength it is in. This time we have to shuffle the formula a different way to find out what energy is. We know the other two values, so from this we can derive that E equals F divided by Q. We sub in our original values to calculate that E equals 2 times 10 to the power of 5 newtons per coulomb in a southerly direction. Equation we'll be using the shuffled version of the volts per meter formula. A point in field 1.5 times 10 to the power of negative 3 meters from the origin point has a voltage of 3.8 times 10 to the power of negative 4. Calculate the field strength. In this question we're given a voltage and a point and we're asked to calculate the field strength. We're going to shuffle our equation and lay it in a linear function. To find the field strength we have to divide the volts by the amount of meters there are. We sub this into our original equation and we calculate to find out that E equals 0.253 newtons per coulomb. Here's a quick summary of what you've learnt. If these seem unfamiliar, please rewatch the video at the point that you need to find the information that is required.